And our first speaker is Tom Rana from the University of Leeds, and he's going to talk about optimal partition problem on surfaces.
So thank you for the introduction, Charlie, and thanks for the invitation not only to come for this week, but I'm also involved earlier in the Newton Institute programme, sort of before Easter time. I've very much enjoyed my time here in Cambridge. Enjoying the talk so far this week, and I hope this will continue starting this afternoon. So I'm actually going to talk about some of the work which kind of looked at whilst I was here in Cambridge, and the start of it is quite a abstract problem. So the problem that we're trying to look at is eigenvalue partition problem. So we're thinking about a closed hypersurface gamma, and we want to try and partition that into a fixed number of partitions, which we'll call M. And we want to do this in such a way that we minimize the sum of the first eigenvalue of the Dirichlet Laplacian over each partition. So one way to think about this is that we have various species, so biological species, living on a surface. We want to try and compete against each other, and so what they want to try and do is expand as fast as they can. So that's the way that you try and minimize an eigenvalue. But of course they're in competition against each other, so you want to try and minimize the sum, so that all the species seem equally happy, or less happy, at the end. So the known cases, so there's some analytic work been done on this. So if you only have one partition on a sphere, you just get the whole thing. That's a good sanity check. If you have two partitions with still not much more work, you end up with just two hemispheres, so the top and the bottom. So already you can see that there's some kind of non-uniqueness built into this problem, that of course any rotation of your sphere is going to kill you straight away, and of course any kind of symmetry in your surface is going to take part in this as well. But kind of removing those kind of things, these things are quite generic otherwise. And then with quite a bit more work, looking at things like half eigenvalues on the sphere, you can end up with a three partition, which is a so-called Y partition. So the angle at this triple junction is 120 degrees. Okay, and so you can work out all the eigenvalues and eigenvectors that correspond to these problems, and everything's quite nice. So I'm really interested in seeing, can we design numerical methods which can first replicate these kind of conditions, and if not, can we then try and take them on and look at higher numbers of partitions, first say up to 10 partitions, but then can we get really higher, sort of towards the tens, hundreds, thousands of partitions. There's a conjecture in the plane that for very large numbers of partitions you get a hexagonal tiling of the plane. Okay, so since you want a closed surface, we know that we won't be able to get a complete hexagonal tiling, so we want to try and see what we get instead. Sure.
I thought that's impossible to have a total hexagonal tiling
of the plane.
Oh, sorry.
Yeah, so the plane, yeah,
Okay.
on the surface, exactly. So that's kind of what we're looking to investigate. So the kind of first stage of this kind of approach of trying to make a computational method is we're going to use a surface finite element method. So we take our surface, which is mainly going to be a sphere in this talk, and just stick a whole load of triangles on it. And we're to represent all our functions by a piecewise linear function over this set of triangles. This is quite generic with respect to the geometry, so you can do things like torus and many other things that you want as well. It's completely generic. So as a first approach, one might think, okay, so we have some domains. So we're going to describe these by a characteristic function phi. So phi will be 1 inside the set that we're interested in, and 0 outside. Then to solve the eigenvalue problem in that set, you can consider this kind of problem. So we have a Laplace-Beltrami operator equals the sort of usual guy, and then we have this penalty term, so we're penalizing our function to be small wherever phi is different from 1. Okay, and so if you try and solve this guy, you can see that computationally you get order half epsilon convergence to the eigenvalue solution. So this seems a pretty reasonable approach given one domain. Now what we want to try and do is now, given these eigenfunctions, eigenvalues, try and minimize the sum. So we consider this kind of vector value of functions, which all take values between 0 and 1, which sum up to 1, and then we try and minimize the sum of these first kind of penalized eigenvalues. And then hope is if we send epsilon to 0, we're going to get the right guy out at the end. Okay. Okay. Yeah, that doesn't work. Okay, so a kind of simple approach to this is that we can try and use a gradient projection method. So the rough idea is we're trying to do something like a gradient flow, but somehow the constraints are all a bit funny. So we'll just do one step of a gradient flow of an unconstrained problem, then project back into the constraint space. So this is equivalent to reformulating this as a variational parabolic inequality and just using an explicit time stepping scheme. So the scheme really boils down to we solve each of the eigenvalue problems for a sequence of phi i's, which are now piecewise linear functions. We end up with the piecewise linear function out at the end. We then update the phi's individually using the variation of the energy. So in this particular formulation, the variation of the energy is the square of the eigenvalue divided by epsilon squared, the eigenfunction divided by epsilon squared. And so we just multiply by a time step as well. A time step parameter, which we will call alpha here. So we can do this nodal-wise. And everything seems to be okay for this. And then once that's done, we can project back onto the simplex so that we're back into our constraint set. Recompute the energy. There's a little bit of adaptive time stepping going on in this as well. And then we test for convergence. And if not, we go back to the start and go through the process again. So each time step, we solve m different eigenvalue problems. There's a small nodal-wise update, a global projection step, and then just some things to make sure we're getting towards convergence. So a key point of this algorithm is that each of these eigenvalue solves can be done in parallel. They're completely independent of each other. So if you're thinking about modern scientific computing architecture, you can use large parallel computing to compute each of these on a different processor, and then the communication only takes place in the projection step. So thinking about this in a practical sense, this scales quite well because the projection is a very small part of what's going on here. Okay. So hopefully you can see these dots in this picture. So if we fix one particular value of epsilon, we can look at the energy at each value of h. So if we find the mesh, we're going left or right here. And we can see that we're getting some good kind of convergence to a particular value. This dashed line is the exact value. So we're using here 3 partitions, so we know what the answer is, so we know how well we're doing. That's where the dashed line is, and we're getting some kind of good convergence in h. Then we can go to the next stage and see, well, what happens if we reduce epsilon and h together. So for different values of epsilon, so this between black to yellow is decreasing epsilon by half each time. So for the first few values, things are going good. The error in the energy is decreasing, so this is a logarithmic scale, so things are going quite well. Unfortunately, if you take epsilon too small, things don't go quite so well. Okay, so as you reduce epsilon, you seem to be picking out bad values. Okay, and the problem that we have with this original formulation is this sort of kind of penalized energy functional is concave in the function phi. Okay, so this means that there's lots of local minima going on. We're keeping getting trapped in local minima. So what can we do instead? One possibility is that we now try and think. Well, so and kind of think a second problem with this method is this: the function phi that we're approximating is also going to have sharp discontinuities. So numerically approximating a characteristic function is not often a great idea. We can try and think to maybe smooth this out. So the first step in this process is to reformulate this eigenvalue problem in terms of the eigenfunctions. Okay. So for each of the eigenfunctions normalized in L2, you just minimize the sum of the Dirichlet energies. So this gives the approximation of the eigenvalues. so it is the eigenvalues, and then we only allow functions which take values in this constraint set now. So this means that each of the eigenfunctions is disjoint. That's what we're going to do. Okay, so you can think of this as a harmonic map problem into a singular set, if that's how you want to think about these things. Okay, and so this problem is totally equivalent to the original eigenvalue problem when you think about things like quasi-open sets. Okay, so then we relax this problem so that we have a penalty term in the eigenvalue problem, so we have a 1 over epsilon squared factor, and now rather than having some funny functions phi, we use the other eigenfunctions as our penalization term. So now we have quite a nice energy that we can try and compute with. Still, the slightly funny constraint, a slightly funny nonlinearity, but things should be a lot better. Okay. So now we want to try and find a way to do this which again scales to a large number of processes. So we do an operator splitting scheme. So rather than solve the eigenvalue problem here, we're just kind of simpling things down to a stage further again. So we just do one time step at the heat equation, which is very simple with a triangulated surface. We then can solve, for the nonlinear terms, we can do this exactly because the ODEs that come out are just linear. And then we normalize in L2. So as before, this first step can be done all in parallel. All the different equations are completely independent. The normalization, again, is completely independent between each of the processes. But then this nonlinear update stage is where we have to do something slightly more sophisticated and communicate between. But here now we have kind of the advantage that we're really only interested in kind of it's the solution of the heat equation which goes into this nonlinear term. So we can do this update nodal wise using the values from the heat equation. So these can be kind of communicated once in a quite efficient way. So again, we start again with fix epsilon. We look at 3 partitions and we see what we get. So over 4 levels of grid refinement, starting from the blue, going through the green, and eventually down to the pink, we see a good convergence to some particular value. Again, we have this dashed line. So this is really saying that for each particular fixed value of epsilon, this approximation of the energy might not be very exact, very close. But as we reduce epsilon, we hope to get a good estimate out of the energy. And then we can look at epsilon convergence. And now, going from the black through to the yellow, we're reducing epsilon, and we can see very good convergence. You can calculate, again, that it's an order half convergence in epsilon for these final iterates. This kind of funny behaviour here is to do with the fact that actually, for each of these problems, we're underestimating the energy consistently when we get to convergence. So the energy will start off higher on the higher grid levels, and then as we refine, the energy decreases, goes beneath the energy. But as you reduce epsilon, the energy increases back up towards its accurate value. Good, so things are all nice there. And then we can go on to look at different numbers of partitions. So, I'm just going to cut here, hopefully show you some pictures of these things with any luck. So for 3 partitions, is kind of indicative. I'll just explain what we're kind of thinking of here with these plots. So we have 3 different partitions here. We have a blue, a red and a green. So we've just cut off each of the eigenfunctions that we recover at a value 0.1, which is kind of arbitrarily chosen just so you can kind of see the separation between. And then they're shaded by the value of the eigenfunction, and I've put some contour lines on to kind of help see this as well. Okay. So for 3 partitions, we recovered things quite well. If you wanted to take a slightly smaller value, you can recover the interface more sharply. But of course, as with these kind of methods at the triple junction, it's a bit harder to define exactly where that triple junction is. So for 3 partitions, you have quite a good representation of what's going on here. So for 4, first one that we didn't know the solution for, we go away, we compute, have a drink of tea. Hopefully things load. Okay. I'll come back to that in a second. Anyway, so when you look at all the pictures for small numbers of partitions, you can see that the partitions always come out to be kind of projections of simple polynomial shapes. So you end up that at each of the triple junctions, the angles are all equal, and all 120 degrees. We have this very simple kind of geometry going on. So for m equals 3, we've already seen that you get these 3 crescent shapes. For 4 partitions, you have 4 triangles. For 5 partitions, we now have 2 different types of shapes. You have 2 triangles at the poles, and then 3 rectangles going around the equator. For 6, you end up with something that looks quite like a projected cube pushed out. Again, for 7, we have this kind of difference. We have 2 pentagons, which are again on the poles, with 4 rectangles going around the equator. Then we get to 8. We, somewhat surprisingly, you might think, see 4 squares and 4 pentagons, which I can't do with my hands. I'll hopefully see the picture in a second. But you can kind of see that there's some kind of general pattern here that as we kind of increase m, we're getting larger number of sides on the polyhedra, the polygons that we recover. I don't know how generic this is, or can't prove anything about this. I think this is kind of some generic thing. And as you increase past this number, the pictures aren't quite so pretty, so I haven't got these and I haven't been through exactly. But you don't see anything that has more than 6 sides. So it seems like 6 is an upper limit. But always in all the computations, you'll always see some pentagons still remaining. So this kind of backs up what we were saying before about you can't cover your surface just in hexagons. So let's see how this guy's doing. That's it. So for 4, so we have these triangles. We have a nice big green one there. You can see this equal angle condition coming through again. And this is the same at all the junctions. So for 5, it's kind of first non-trivial shape that comes out. We have a rectangle there. See if I can get this right around. That's the second rectangle, third rectangle, and then we're back to the start. And then on the 2 poles we have this blue triangle and the green triangle. And again you can see this kind of equal angle condition at all the triple junctions as well, all the way around. So for 6, you have this nice kind of cube-like shape, nicely projected out. Again, we have these angle conditions, and things really do look like quite regular polygons. And what's going on here? So again, we all have these nice angles. So So I've dropped some of the contours on this to try and just make the shape a bit clearer, but here you can see big red pentagon on top. And as you look around the sides, and hopefully show. Here we have all rectangles around the equator. Again, the nice angle condition and a pentagon at the other pole. Finally, the most interesting one. Come on. So the pentagons that you see around the equator are all now kind of short and fat and matching up along the short edges, going round, which leaves room for two rectangles together at the poles. So I don't know if this is kind of counterintuitive or there's some kind of intuition for this. One might think that with an 8-sided regular polygon you might get an octahedron out. This is not what we see here, and this seems to be the true minimizer. So I don't know. But again, we have these angle conditions which might suggest that the octagon wouldn't be optimal because then you'd have 4 partitions meeting at the 2 poles.
Can you do 12?
Yeah, I don't have the pictures. So I've run computations with this up to about, so I tried 128. That doesn't quite converge in time. 64 does nearly converge. 32 is just about okay. And I can do 16 reasonably as well.
Do you get 12 pentagons for 12?
I haven't counted round. I haven't counted for more than this. If there was a nice way to kind of automate the counting, that would be brilliant.
But they're always trivalent. I mean,
yeah, so there's always triple junctions, and there's never more than 6 sides. So if there's something to prove there, go ahead. And I'm saying this is quite generic, so if I remember the name. You can do this on the torus. And on the torus now we don't have constant curvature. So although we have kind of, this looks a bit more symmetric, so we have the 4 partitions around the top and 4 around the bottom. Where we have these triple junctions, we still have this kind of equal angle condition here around the outside, and then things on the inside as well. So these properties seem to be quite generic, independent of the kind of curvature and things that are going on around them. So I don't know what you can prove, but these are the things that we've found here. So kind of just to go back to this guy. Yeah, so these are the list of shapes we get out, and we have estimates of the eigenvalues that we get out of this process as well. So you can see that the eigenvalues are clearly growing as the shapes become smaller. Okay, so to really get into higher numbers of partitions to get things to work more efficiently, we have to consider ideas such as adapting the mesh. So a kind of common idea in these kind of phase field approximations is that you adapt to the interface. So here's kind of an example where I was computing with 8 partitions on a sphere. So this is the kind of the part where our eigenfunction is positive, and we've adapted to the interface between all the partitions. Okay, so this actually works quite well. You get quite a good estimate of the eigenfunctions because you're able to take epsilon quite small by doing this kind of approach. So you're resolving the interface very well. Which is all very nice, although you can see that this black region, this eigenfunction is 0. So all these extra degrees of freedom that you've put in here are pretty much wasted. So as an alternative approach, you might want to try and think about using a mesh where you adapt to where the eigenfunction is positive. Of course, if you do this, then you break the assumption that the grid was the same for each of the different equations. So now all of a sudden the communication between the processes becomes more expensive. So what I'm trying to explore at the moment is which kind of these adaptive schemes will allow us to go up to sort of more, get good convergence results up to say 100 partitions, and see if we can go beyond that as well. So that's what I'd say. So thank you for your attention.
Is it time for questions? Yes?
Yeah. I think this also may have an application in sort of three-dimensional networks that have this trivalency, like ohms, and things of that sort, where there are these questions about a polyhedra that make them up have certain sort of variance, and you're sort of exposing them, whether the faces are rectangular, triangular, or what have you. And depending on the sort of energy penalties that you put into the system, this might be a nice way to find out in a network, which typically runs from about n equals 4 faces up to maybe 40. It's about as, that would cover most realistic three-dimensional networks. Maybe this scheme will tell you what the most energetically favorable combinations are.
Yeah, I was speaking this morning to Doreen Bakor. He was asking about this kind of three-dimensional problem. And he was saying that there's various things conjectured in 3D, which they have no real idea. So at first they thought this kind of regular tiling in 3D for this kind of problem would hold again, until some chemists came up and found that there's actually a more, it's kind of 2% more energetically favorable partition, where you have 6 of one type of object and 2 of another. And then that's all periodically repeated throughout. So I definitely think that these methods would work in 3D, and I think they're actually quite extendable quite directly, although some of the parallelization you might kind of think about 2 dimensions.
But the spherical net is equivalent to a polyhedron.
Yeah.
All you have to do is change the dihedral angle across those edges, and you can make everything from the spherical net all the way over. I think there's an extreme limit to the dihedral angle of 120 degrees. And in a real network, they tend to be 60. So I think it might be interesting to look into that application.
That'd be good.
About it.
Sure, that'd be good.
If there aren't any more questions, then let's thank Tom again.